Hello everyone, and thank you for attending today's webinar, Modern XRF Solutions for Thin Film Measurements on the Bench and in Process Control. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your audience console are several application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget at the bottom and submit your question. We'll try to answer these during the webcast, but if a full answer is needed or we run out of time, you'll receive an answer later via email. We do capture all questions. A copy of today's slide deck and some links to additional materials are available in the resource list widget that looks like a green folder. You can expand your slide area by clicking on the Maximize icon on the top right or by dragging the bottom right corner of the slide area. If you have any technical difficulty, please click on the Help widget. It has a question mark icon and covers common technical issues. Now I'd like to introduce Dr. Bruce Scruggs, who's our presenter for today's webinar. Bruce is the XRF product manager at EDAX and has been involved with XRF for 17 years since joining EDAX. He holds an undergraduate degree in chemistry from Valparaiso University and graduate degrees in chemical engineering from the Massachusetts Institute of Technology. He started out working in applications for a company which builds innovative sample handling equipment for solid-state NMR. Bruce got involved in XRF when a headhunter confused RF radiation with X-ray radiation, and the rest is history. While at EDAX, Bruce has also been the product manager for service, working to improve the quality of service and speed of response times. So with that, I'd like to hand over to Bruce.
Good day, everyone. Thanks for that introduction, Sue. Again, my name is Bruce Scruggs, and we'll be talking about XRF solutions for thin film measurements on the bench and in process control. Quick slide to discuss the overview of the agenda. I think we all know the focus for the basic talk. What we're going to do is I'll give you a one-slide description of X-ray fluorescence spectrometry. We'll talk about the advantages of the technique, and we'll go through some of the basics of the measurement, the accuracy, precision, typical measurement times, the errors associated with these kinds of things. I'll show a few slides on a product overview of the EDAX products in this area, and we'll go through some examples that we've measured. So one slide on theory. This is a little bit busy, but this basically covers the production of X-ray fluorescence signal. What we have here is the Bohr model for the atom, for an element. In the center, you have the nucleus in red. And then you have all these various electron orbitals. You have a K orbital in blue, the L orbital in green. You have the M orbitals in, I guess that's magenta. And what we do is we shine X-rays down onto the elements in the sample. And these X-rays excite the electrons and eject an electron from a certain orbital. So if we eject an electron from the blue orbital, the K orbital, you create a state where you have electrons from the lower energy orbitals, the L and the M series, relaxing back into the K series. This generates a characteristic X-ray for that element. When you have electrons relaxing into the K orbital, that's called the K-line series. When you have them relaxing into the L orbitals, that's called the L-line series. And when they relax into the M-line from even lower energy states, that's called the M-line series. So we have a variety of X-ray lines, K, L, and M, that are characteristic of a particular element. The overall advantages of the technique, because this is X-ray, it's non-destructive. We use low-power X-ray tubes. It's non-contact. We can typically measure materials as is. The technique can be adopted for an air or a vacuum atmosphere. We generally measure elements, or we say we measure elements heavier than sodium. This depends on a lot of different factors. One, measurement atmosphere. In general, we use vacuum to measure sodium and magnesium, aluminum, those kinds of elements. Sample loading. If the sample is heavily loaded with something, then our sensitivity for that element is obviously better. The amount of area that we're exciting, if we're trying to, if we have to focus on a very small area, this may affect our sensitivity for certain elements. If we're allowed to measure over a larger area, let's say for blanket coatings, it's possible to get more sensitivity to a wider range of elements. And of course, measurement time. The longer we measure for, the more sensitive we are. This is just a quick slide to show you some of the basic components of what we use for an XRF spectrometer. Our X-ray excitation is a 50-watt tube. As X-ray tubes go, this is a pretty low power tube. We use different metal targets in these tubes. Rhodium is a typical target that we'll use. Molybdenum is another target. Chrome is another target. And each one of these kinds of target tubes has different excitation efficiencies for certain sets of elements. Rhodium is what we typically use as our general go-to all-purpose X-ray tube. Our X-ray detectors are silicon crystal-based detectors. For those of you who may be familiar with the technology, maybe 10 years ago, 20 years ago, we were using lithium-drifted silicon. These required cryogens like liquid nitrogen to get very cold temperatures on the crystal. Today, we're using simple silicon wafers, and we cool electrical cooling. So there's no cryogens needed in the detectors of today. It's a very robust design. In general, we're using X-ray spectrometry to measure single and multi-layer stacks, to measure bulk materials, and to measure trace elements in bulk materials. So we have 2 poll questions, and here's our first poll question for the audience, if you'd be so kind as to check the responses. The poll question is, what types of coatings are you measuring? And of course, we recognize that it's possible that some of you are here just as a new introduction to XRF, so we have an option for don't currently use to measure coatings at all. We have a variety of other ones. You can check more than one. Option, and we'll give the audience maybe 30 seconds to respond to this one, and then we'll have a look at the results. I've just got maybe another 10 seconds to go. Okay, so let's see what the poll results are. Okay, we have a good bit of the audience that has not used XRF to measure coatings at all. And electrical protective coatings. Okay, all right, very interesting. All right, XRF spectrometry in terms of quantification. We're going to talk a little bit more about this in some later slides as well. What I wanted to do here was to touch on that in the quantification methods that we use, we start off with what's called a fundamental parameter modeling type process. And this starts with a very basic physics approach. We know what elements are in the sample because we've identified the peaks. When we measure coating layers, you need to define which elements go into which layers, and that's typically well known when you're measuring something that comes out of a process or something that's been made in your factory. Sometimes you find some surprises, but in general, you define what elements are in what layers, and we use a physics-based computer model to calculate the compositions and thicknesses of the layers. Fundamental parameters stems from the fundamental parameters of a particular atom, characterizing things like excitation efficiency, and that's where the name comes from. Of course, we can input very simple standards to just characterize the geometry of the system, or we can go all the way up to using a type standard, where that type standard is matched to the kind of material that you're measuring, and this can give us the best kind of accuracy. One of the nice things about this sort of quantification is that it gives you more stable results even when you're outside of where the quote-unquote calibrated range of the model might be. And even when you're outside of that range, you may not get the best accuracy, but it gives you some general idea of where you are with respect to where you'd like to be, particularly in terms of process metrology. So you may start up a particular process, not be producing the material in spec that you want, but you want to have an idea of where you're at. So you may be outside of the calibration range, but it gives you basic guidance on how to tweak the deposition parameters to get you into spec and making production grade material. Okay, precision. XRF spectrometry we're measuring X-ray photons in this particular case, and the more time that we wait, the more photons that we get into the spectrum. So the precision is a function of the peak intensity, and our peak intensity is normally displayed as X-ray counts per second. That way, no matter how much measuring time we use, we always have a certain set rate, X-ray counts per second. The total X-ray counts in any given peak is the measurement time times those counts per second. Now, the precision is a function of a variety of factors. The heavier the sample loading, the stronger the signal peaks, the better the precision. The larger the excitation area in general that we excite, the more signal we have going into the detector. I mentioned to you that we can use different sorts of X-ray tubes with different metal targets for certain kinds of applications. We may select one over another for certain applications to improve the excitation efficiency and measurement time. The longer we measure for, the more counts we have in the spectrum, the better precision we have. As a function of measurement time, precision is the square root of the reciprocal of time. So basically, the longer you go in measurement time, the lower the precision number is, which is actually better in this particular case. And it's a square root factor. So if you measure 4 times as long, your precision improves by a factor of 2. Typical measurement times in the area of coating thickness run about 30 to 60 seconds. Okay, here we're looking at sort of a general cartoon of thin film measurement range. And on the x-axis, we see film thickness. On the y-axis, we have the X-ray intensity. And then there's a little cartoon showing a yellow layer on top of a cyan substrate layer. And in this particular case, we're measuring the direct emission signal coming from the coating. And what we use is a certain energy line of X-ray that as you get to, as the layer thickness grows, so does the X-ray intensity. And you can see as we first start out, there's roughly a linear relationship that defines that thin film region. As we increase in thickness, we don't get the same gain in intensity. And what happens at a very thick layer is that we reach a saturation level, an asymptote. That's because at that particular level, no matter how much more coating that we add, we are not detecting any more X-rays coming from that layer because we've reached the escape depth limitation for that particular line energy. So if we pick a lower energy line, we're going to only be able to measure thinner layers because the X-ray is weaker. If we pick a higher energy line, we can measure thicker layers because those those X-rays have a better capability to go from a farther depth. Okay, this slide shows a table of general measurement range for different sorts of elements. So let me go through a little bit of a few of the columns here. So on the left, we have different elements, their atomic numbers. And on the right, we have K lines, L lines, and M lines. K lines are our most energetic lines, then L lines and M lines are the weakest. So if you look at the first top group of 4, these will generate K lines in our types of X-ray equipment. We generally won't see the L lines or the M lines. The L lines in some of these will be generally too weak for us to be useful. And you can see that the K lines, here's some rough idea for a single layer, the nominal maximum thickness that you can measure. As you go to the next set of lines, from molybdenum up to tin, you can measure with K lines or L lines. The K lines will allow you to measure much heavier layers, anywhere in the range from something like 50 up to around 100 microns. The L lines being lower energy, you can measure much thinner layers. But for those very thin layers, you can have better sensitivity to changes in that layer thickness. Now, as you reach the, let me quickly cover the last few elements here. In the platinum to lead series, there are K lines that exist. It just happens to be beyond the detection range of the types of detectors that we use. So we focus on the L lines and the M lines. And you can get some rough idea of the kinds of thicknesses that you can measure. One thing I should mention, when you're close to the maximum range, when you're out towards the asymptote, what you'll see is that if you're looking up in the X-ray intensity range of the normalized range, up around 0.8, 0.9, if you interpolate over to a position on the graph, what you'll notice is that small changes in X-ray intensity will create large changes in thickness because you're out on the asymptote at that particular point. So that's where that effectively defines the usefulness for X-ray, is when you're too close to the asymptote, maybe around 90% of the total maximum thickness. Your results you'll lose precision because you'll be jumping around on the plot as you have small changes in X-ray intensity. Okay, so this table again was just to give you a rough idea of the kinds of thickness ranges that we can cover. We can go from very thin layers all the way up to relatively thick layers. It depends on the elements that you're looking at and the line series that you're looking at. Okay. We can also measure multiple layer stacks. This requires a little bit more complicated modeling, and you have to have good control over the accuracy of the top layer, because errors when you calculate for the top layer in the computer modeling, they percolate down into the lower layers. I just wanted to show here some typical multi-layer stacks that we measure. The first example, photovoltaic absorbers. So the absorber layer might be, a couple of microns at the most, and there's typically an electrical back contact layer, which is also critical to know to have good performance. So these are generally made out of molybdenum. They're around 300 nanometers thick. And another typical area, electrical contacts. If you remember the poll survey, there were quite a few respondents checking off the electrical area of measurements. One of the important things to measure there is the gold thickness. They want the right amount of gold thickness to do the job, but you don't want to put too much gold down because it costs a lot of money for that. So here's some typical multi-layer stacks for electrical contacts. And we'll have an example of electrical contacts later in the presentation. Okay, so a quick review of the EDAX instrumentation in this area. We have a benchtop unit, which we call the SMX Ben on the left, and a process control tool, which we call the SMX ILH on the right. The ILH unit is an inline unit, which you can build around a conveyor, or you can have a manual feed tray in the unit. The benchtop unit is something you can use in the laboratory, both to do general QC, QA, and to support the inline unit out on the factory floor. The benchtop unit, the measuring head includes collimators and filters. The collimators basically define your beam size that you're measuring at. The filters provide for you some beam conditioning. You can improve excitation efficiency in this way, improve the peak to background for certain elemental ranges. We have a programmable XYZ stage, so you can automate measurements, and it's done all in an air atmosphere. Typical uses for this would be the process and recipe development for startup processes, for supporting the inline unit out in the factory floor, for looking at layer formulations, for doing offline work, small scale quality control, for doing R&D. The ILH unit shares the same kind of measuring head as the benchtop unit. So when we build calibrations on the benchtop unit, we can port them out onto the ILH unit and maybe do a little tweaking on them, but we get a good idea of how is the inline unit going to perform based on the benchtop unit's performance. Again, it has collimators and filters as the benchtop unit. The programmable XYZ is done on the measuring head. Typical automated sample loading is done by a conveyor system, which would be incorporated into the factory floor. Measurements are done in air, again, and we have an optional feature where you can measure at ambient, or we can also measure high temperature. And we want to be able to measure in high temperature in case the deposition process heats the sample up, and we want to measure in real time. We don't want to wait for it to cool down. So we have an optional feature to be able to shield the measurement components from the hot sample. Ideal uses for this: we can measure stationary panels and do point-to-point measurements. You can have moving panels or streaming substrates where you can get average values in a particular location on the panel. You can use it inline, post-process. You can use it for flexible substrates or rigid substrates such as glass, or the flexible substrates you can use steel, aluminum, polymer. The substrate can be anything really. The control software for the tool is really designed for a production type environment. It's recipe based, so you can build a recipe. A supervisor could build a recipe. An operator could load those recipes and run them, and that operator can be at the system, or that operator could be somewhere in a control room working over the factory network. Results can be sent out as flat files, or they can be loaded or they're updated in an SQL database so that the factory system can access that database and pull it into its own databasing system. It also has a leveled approach for the software where you have different logins. So you have an operator login, which allows you just to load these recipes and run them. You have a supervisor level, which allows you to create recipes, build calibrations, and create them for the operator to use. And you have a maintenance level, which allows you access to all the functions. Okay, we're going to return to the subject of calibration. And again, we're using a physical modeling of the system once we've defined what elements are in what layers. And we can use simple to type standards to go ahead and create a calibration. So what kinds of standards do we use? Just to give you, this is a good topic to discuss, to give you a basic idea of the kinds of things that we use in this case. When I say simple standards, I really call them something like a pseudo-type standard because it's not matched to the particular sample that we're measuring. We know what elements are in the coatings. We can choose pure element materials, maybe 99.9% pure. So let's say I wanted to measure gold on nickel on copper. Well, then I could pick pure elements of gold, nickel, and copper, and I measure each one of them. And I tell the software, okay, this is a bulk material. Generate a calibration coefficient for me for that particular element. Or if a particular element isn't stable or it's toxic and nobody wants to handle it, you can also use compounds. So as an example, we could use potassium carbonate to get a calibration coefficient for potassium. Now on typical single layer materials, maybe relatively thin, we can get accuracy using this type of method 10% or better. And I mention this because a lot of times we'll get coded samples in and we'll be asked to do some demonstration measurements for these, and we don't have type standards for them. It could be something that's a little bit more proprietary in the factory, and so what we'll typically do is we'll fall back and we'll find pure elements and compounds and come up with calibration coefficients for those. We can always improve upon that accuracy that we get there by using more of a type-matched standard. Now, type-matched standards, there's a lot of commercially available ones for coatings that are widely used out in industry. So, for example, electrical contacts, electroless nickel. These are commercially available materials. A lot of pure element type coatings, gold, nickel, palladium, silver, tin, you name it. It's very easy to make foils out of these, and that's generally what they'll use as a commercially available standard. They will also make hard-plated standards. Hard-plated standards tend to last longer, but they're very specific to one particular coating stack. Metal foils, they're stackable, so they're flexible in what kind of a coating you can build up, but they tend not to be as durable because when you've got 1 micron gold foil, it tends to be a little bit delicate. Other types of type standards, if you're working with a proprietary formulation within the factory or as a product, you're obviously not going to find that commercially available. It's proprietary. And in this particular case, this is where you would need to have an effort to internally develop standards. That is, you produce something and then you conduct some sort of a qualification process to determine what the values of composition and coating thickness for that are. My comments here on that would be that if you're making something out in the factory and you want to create standards to measure those things to the best accuracy possible, then I would use the same methods that you're doing out on the factory floor to make those samples. You don't want to make something in a small batch that gives you a slightly different material, a slightly different density than what's going out on the factory floor, because your results will be different. So you should make it by the same processes that you're making your production material. In a case like this where you have type standards, your bias, your error can be better than 2%. It depends on the composition and thickness range that you're trying to cover. If you want better accuracy, you can always build models over smaller thickness ranges to provide you with better accuracy. Okay, I'm just waiting here for the slide to update on my screen. It's a little bit slow. So hopefully this is updated on everyone's screen. Let me so what we should be seeing here is, look again, there it is. There we go. Slight glitch there. Okay, so what I thought I'd show you here is an example of a calibration example for a very simple coating. So we had a blanket coating of indium on an 8-inch wafer. And the deposition process for this masks off the outer couple of millimeters of the wafer. And the idea was to look at the wafer and see, well, how homogeneous is the coating? So I wanted to try some different calibration methodologies. So we created type standards by taking the wafer and using a focused ion beam microscope to mill away a certain section of the coating and look how thick is the coating in that particular area. We look in the center, we look out at the edges where we might expect to see gradients in the coating thickness. And so then I choose the center portion of the wafer, and I use that as my type standard. So if we go down to the table here, I've measured in the center, and then I've measured certain distances off of the center all the way out to the outer edge. And the first column on the left is the fib results for thickness, And you can see there is, when you get out to the very edge of the wafer, you begin to see a decrease in the thickness. So what I did in the second column to the left is I used the centerpiece, the center measurement, as a type standard. I go ahead and I say this thickness for this X-ray intensity is 6.6 microns thick. And we look at then the results as we go out close to the edge. As you go down the list closer to the edge of the wafer, you can see it's relatively uniform in the center. And again, it begins to show a gradient out toward the end. Now, when we first looked at this wafer, I didn't have a type standard. I hadn't done any focused ion beam measurements of the sample yet. And so I used pure elements. And the very first time we did it, we didn't have any pure indium in-house. It's not an incredibly common element, but guess what? Tin is very common, and we had pure tin in-house. Tin is very close in X-ray energy to indium. So I said, first, why don't we measure tin, and we'll call that the calibration coefficient for indium and see what kind of result that we get. And you can see that it was within, if you compare the fib result to the tin result, we were within less than 100 nanometers, which to me was quite a good result. We also bought some indium and said, okay, let's do the same test with indium. And you can see, again, we're within 100 nanometers. And the two are slightly different than one another, but in reasonably good agreement with the fib results. So I was quite encouraged to see in this particular example anyway that our accuracy even with pure elements on a relatively thin layer were quite reasonable. You can see that our differences between the indium all along the layer are roughly within 50 to 100 nanometers of what the usage of the type standard is. This is because it's all simply based on the X-ray intensity that we're measuring. Now, one comment I have about the fib results compared to the type standard, and I think this is a good comment when you talk about the error associated with what you're using as a type standard. The focused ion beam measurements were milling a very small trench, maybe 10 microns wide, into the sample and looking down into the trench and saying, this is how thick the layer is. In the X-ray measurements, we're using a 2 millimeter collimator to generate a 2 millimeter spot and making an X-ray and making a coating thickness measurement on this. So the area between where we're measuring between X-ray and fib are quite different, going from 10 microns in the fib to 2 millimeters on the X-ray. What I noticed when we were looking at these, when we were looking at the wafer in the focused ion beam microscope, you can see topography in the coating thickness because this layer is getting thick enough to the point where we're forming crystal grain structure in the indium. And depending on which crystal grain you're looking at, there's a variation in the thickness there. So what I'm getting at is that there is more error associated with the focused ion beam measurement than what I would have originally thought. I'm getting more of an average value using the X-ray. I'm going to get more fluctuation in what I see in the focused ion beam measurements. And I would say their fluctuation, and depending on the grain structure that we're hitting, is probably around 100 to 150 nanometers. Versus if I'm just looking at the image of the coating thickness and constantly recalculating that, and how I set the cursors on where's the beginning of the coating thickness and the end of the coating thickness, that's a much tighter range. So as I thought about this problem, I realized there's a much larger error associated with using the fib to generate type standards. But it was definitely a good first attempt. Okay, we have another poll question for the audience. Where are you currently using XRF to measure coating thickness? And the choices are you using it in the lab, QC, QA, failure analysis, process control, you're planning to use it, you're currently not using it at all. You can check multiple responses to this if you're using it in multiple places. So again, I will give another 30 seconds or so to respond to the poll question. We've got another 10 seconds to go. Okay, let's go ahead and see what the poll results are. Okay, all right. Many people aren't using it at the current time, so I hope that this webinar can provide you with enough information to be able to plan on using it in the future. There's more people, of course, using it in the lab than in process control. That would totally be expected, and there's a few people on planning. Okay, excellent. Okay, so I touched on this particular subject when we looked at our calibration example, and I talked about some of the error associated in the kind of type standard and the method by which I was making my type standard, that is the focused ion beam. In general, one of the questions that comes up when we make these kinds of estimates, when we make these types of measurements, is what's the accuracy or the error associated with that measurement? I want it to be a certain value, and that's all associated with the instrument. And one of the main reasons for putting that slide up is to say, well, that error is not necessarily associated with the instrument or the modeling methodology. The components that contribute to error in your measurements include the error associated with the type standard. It's not known to an absolutely singular value. There's always a tolerance on what that value can be. There is a certain bias in the modeling. Perhaps in a certain area of the calibration curve, it's not as good as it is in another area. We measure a number of samples and come up with an average bias value, that kind of thing. There's also associated with each measurement, if you're doing a single measurement, there's always a standard deviation associated with that measurement, and you can characterize that value as well. Now, the total error is going to be, the technical term is summing this up in quadrature, but in layman's terms, this is basically the error is equal to the square root of the sum of the squares of the different contributions to the error. So in this case, what we would do is we would sum up the squares of the error in the type standard, the error in the bias of the measurement, the error in the standard deviation. We'd sum them up, the squares of those, and take the square root, and that'll give us our overall error. Now, the standard deviation and the bias, those are associated with the modeling methods and the instrumentation. Standard deviation, for example, can be characterized by making repeat measurements and determining what's the standard deviation in my measurement. I can minimize that standard deviation by improving my excitation efficiency, by measuring for a longer period of time, by making some repeat measurements on the sample at that same position. My measurement bias can be minimized maybe by optimizing the range of thickness and composition measured. If I really need to have the best accuracy, I might want to shrink down the measurement range that I'm making, or have a few standards that cover the whole range of the measurement that I'm trying to measure. Now, the overall error can never be better than the error in the type standards that you're using. And typical error associated that I've seen associated with metal foils in commercial standards is around plus or minus 5%. Now, you come in and you ask the question, well, what if I'm not using type standards? Let's say, what if I'm using pure elements? Okay, well, there's no type standard, so there's no error in the type standard. The error gets transferred to the bias then in the measurement model that you're using. So what I would expect is when you don't have type standards, the error bias goes up. When you have type standards, then the error is dominated more by, or can be dominated more by, what's the error in the type standard that you're using. And that was why I like the calibration example, because we had a little bit of a discussion about what's the error associated with how I was creating those type standards. Okay, so now we're going to take a look at a bench example here. And we're looking at electrical contact, and this is some kind of a solder lug. It's tin plated on nickel, plated on an aluminum alloy. And the goal was to measure the tin-nickel thickness. And what we discovered early on in measuring this is that we didn't have just nickel plated on there. There was a significant amount of zinc and copper associated in the nickel layer. So we created a calibration model for this. We used commercially available standards for tin, nickel on aluminum. And we also measured some zinc and copper pure elements to give us calibration coefficients for those. Okay, so we measured the top of this loop, we measured the base of the loop, we measured the front side, the back side. To start off with, we look at the result measuring the front side at the top of the loop. The spec for the tin is 5 microns plus or minus 1. The spec for the nickel is 2 microns plus or minus 1. We see nickel is in spec, tin is out of spec. You can also see in the far column on the right there what the composition of that nickel layer is, and there is significant amounts of copper and zinc in it. Were those meant to be there, or were they impurities? I really don't know. If you compare the measurement now on the top of the loop to the base of the loop, what you'll see is that the nickel layer gets thinner. The tin remains about the same. And you'll see the composition of that nickel layer with the copper and the zinc changes dramatically. There's quite a bit more zinc in it now at the base than there is at the top. And we look at all the results now. So on the left, you have the front side. On the right, you have the back side. And you can see that in comparing front to back, the tin layer actually got thicker. The nickel layer is nominally the same and shows the same basic characteristics when you go from the top of the loop to the bottom of the loop. So this was just to give you an example of what you can do with benchtop equipment, looking at, say, electrical layers at a typical component. And maybe there's something about this analysis that says why the part works or why the part is not working in a particular function. So we're going to describe now some applications in process control types of environments and some differences in the different kinds of process control applications. In general, we always ask the question, why are we measuring the process? If it's not that critical to control something, there's no need to measure the process. If you find that there's some parameter that you need to control very tightly, it becomes important to measure the process. So there's always basically two factors here, reducing costs and quality control. We reduce costs by minimizing process startup time and reducing out-of-spec product scrap. Quality control, maybe you need a certain performance or certain reliability, and these sorts of measurements help you to optimize and maintain control within a certain level where you have the right performance and the right reliability. Okay, one area where XRF is very commonly used is in thin film process control for photovoltaic layers, battery components, seed coatings, that kind of thing. Here's an example where we are measuring copper, indium, gallium, selenium photovoltaic absorber layer being put down on a flexible steel substrate. There are 3 measurement positions going on here. We measure one position at a time as this steel substrate is streaming by. We'll measure one edge, we'll measure the center, we'll measure the other edge, we'll go back to the center, and so on. We'll move the measuring head back and forth as it's streaming by, and we'll get an average value in each one of the positions along the width of the web. The goal was a plus or minus 5% similarity between all the different measuring positions. And it's good enough such that you can't really tell the difference between the 3 measuring positions. The black line data points are selenium, green is copper, red is indium, and the blue is gallium. We were making 30-second measurements. This was a high temperature right after the deposition, so we were taking advantage of the ability of the heat shield to make high temperature measurements. Our web feed is about half a meter per minute, so we're getting average data points that average over about about a quarter of a meter. And this can also be used to tell when we're out of spec for startup adjustment guidance, that kind of thing. Another photovoltaic absorber example, CdTe. This is typically plated on rigid glass panels. So here we're measuring the photovoltaic absorber on top of a transparent conductive oxide layer on top of the glass itself. The overall goal here is that they dope the CAD towel with something to give it a photovoltaic capability, and the way that dopant is introduced, the amount of dopant, tells you the efficiency of the photovoltaic absorber. These kinds of formulations generally are proprietary. That's why we don't discuss numbers in these particular situations. Another example, these absorbers are put down onto the, I mentioned this previously, onto the electrical contact, which is typically created from molybdenum. Molybdenum doesn't plate very well on top of stainless steel when you're trying to make a flexible substrate here. So they use chrome on top of stainless to create a seed layer to be able to deposit and get good adhesion for the electrical back contact. Now, the stainless also contains chrome. So this becomes a little bit more of a difficult situation. You have to determine the composition of the stainless, how much chrome is in it, and then we account for that in our modeling, and that allows us then to determine the chrome layer thickness as well, and as well as the molybdenum thickness. And so the modeling in the system was used to measure chrome seed layers around a couple hundred nanometers. The moly back contact are also around a few hundred nanometers as well. Other coating treatments put down on aluminum and plastics. There's a wide variety of these sorts of surface treatments out there. There's corrosion and wear protection in food and beverage, automotive, aerospace. We were measuring recently some metal oxide treatments on aluminum, different kinds of aluminum. One treatment was used in beverage can production. Other treatments were used in the usage of automotive aluminum. Complex multi-element compound treatments, different kinds of salts associated with a surface treatment. Electrolytic nickel is a very popular coating. This is done to coat very complex part geometries. Originally, it started out with a nickel phosphorus type of coating. It's important to know thickness as well as how much phosphorus is there. That generally tends to affect the hardness of the coating. Since then, they've developed a lot of different electrolytic nickel coatings, including copper, iron, molybdenum, tungsten, and these elements and their composition affect the hardness of the nickel coating. These are very typically done on flexible substrates and sheet stock, so flexible steel, flexible aluminum, plastic as well. So these are typically like roll-to-roll type treatments. One last example, measuring coating thickness on medical implants. You'll typically have some sort of a titanium alloy. These are commonly used in making metal implants for artificial hips, other artificial type joints. It's necessary to put the coating on top of these. These are typically grown. They're typically grown as oxidized layers or carburized layers from the base metal material. They provide corrosion protection and wear protection to the medical implant, as well as sort of a chemical seal or a barrier to prevent metal ions from leaching out from the implant into the body. In this particular case, in contrast to the other examples that we show, it's important to measure all of the parts due to a product liability issue. Okay, and also what's different about this typically is that they are growing, let's say, oxide or carbide layers from the underlying alloy itself. So the coating contains the same elements as the alloy. However, in an oxide layer or a carbide layer, because the elemental density is lower than in the metal layer, the thicker the coating becomes, the lower the XRF intensity measured, because the elemental density is less. So we were looking at a particular example where we're measuring in the nominally 10, 20 micron range, and you can see that as the thickness increases, our XRF intensity drops. And we take advantage of that change in intensity to create a calibration curve for thickness. So this is more of a specialized model, more something of an absorption model where we're looking at what's happening with the underlying substrate signal as well. Okay, I think that pretty much concludes the webinar. Just to highlight a few points. XRF spectrometry, it's non-contact, non-destructive. That's a very big advantage in making coating thickness measurements for process control or on the bench. You can always take that part and measure it by another technique, and it hasn't been changed by our measurement method. It's ideal for measuring metals, metal oxides, metal nitrides, metal carbides, pretty much anything in the inorganic portion of the periodic table. You can measure single or multiple layer structures. And EDAX has a very flexible product line. We have tools that can go inline, at line, on the lab bench. The ILH product is very adaptable to different process dimension sizes, to the feed requirements, to how the factory network control is required. And we can measure at ambient or at high temperatures. And with that, I'd like to thank you for your attention, and we will have a Q&A session at this point.
Just to give Bruce time to take a look at the questions that have come in, I just would like to remind you that an on-demand version of this web presentation will be available later today using the same audience link as was sent to you earlier. You will actually be receiving a follow-up email including that link again. And now it looks as though we've got some interesting questions coming in, so I'll hand you back to Bruce.
Okay. So the first question is how big a sample size can be put inside the XRF machine? The benchtop units have a stage travel range of around 200 millimeters. The chamber is a bit larger than that. So you can basically get full coverage on an 8-inch diameter sample. You can put a slightly larger sample in there, maybe something like 250 to 300 millimeters, but then you aren't necessarily able to get full coverage range over the whole sample. The ILH units, they can accept samples up to something like 1.5 meters approximately. So it's on the meter scale as to what they can accept as a maximum sample size. Okay, so let's go to the next question. For the SMX ILH, what is the highest temperature which can be handled? So the heat shield in the ILH system works up to about 300 degrees Celsius. And what it basically does is help to dissipate the heat emanating off of the sample so that temperature fluctuations don't affect the detector and electronics technology. Okay, let's see. Next question. Can metal oxides and metal layers be differentiated? Can elements, oxygen be measured, or only elements of sodium and up can be measured? Okay. We do not measure oxygen in the sample directly. We can only detect directly depending on the atmosphere and the excitation conditions, starting around sodium and up. In an atmospheric kind of system, we can generally detect around potassium and higher. However, there are other sorts of methods depending on the exact sample system that we're looking at where we may be able to measure lighter element coatings. And let me provide you with a very quick, brief example. Let's say that we were coating aluminum on top of nickel. We're probably in an atmosphere-based system. We're probably not going to have very good sensitivity to the aluminum because it's very low energy. And so we probably won't get very good precision in a measurement like that. However, we can detect the nickel very easily. So generally what we would do in a situation where we're measuring some sort of a light element, or let's say some sort of organic-based coating, depending on the circumstances, we might look at trying to measure the absorption of the substrate signal in the coated layer, as opposed to looking at the direct signal from the coated layer. So we have some flexibility in the kinds of things that we're able to do. Okay. Yeah. As another example of that, we were in the medical implant example. We were looking at the metal oxide layers. This is sort of a variation of that, where we're now looking more at how the substrate signal is being absorbed going through the metal oxide layer, as opposed to measuring directly the metal oxide signal itself. Okay, let's see. Here's another question. What is the minimum element content in percentage that can be detected? Yeah, this is a good question. Although it depends on the circumstances and the elements that you're measuring. Typically, if it's elements that we can, if it's something like you're trying to measure nickel, iron, that kind of thing, we can get detection limits that are better than 100 parts per million. But it really depends on what's the measurement kind of application. For coating thickness, we're generally looking at the major components in the alloy versus looking for trace elements. So in coating thickness, we might be looking at a few, quantifying a few percent of a dopant in a photovoltaic absorber. Then there's another question, what is the maximum element content in percentage that can be detected? And that's up to 100 weight percent, but there's a little bit of a practical limit on that because as we get close to the 100% range, there's some variation on that. But in principle, we can go up to 100 weight percent for that. Okay, let's see. One last question. Can you control the depth of measurement using X-ray fluorescence? Okay. Yeah, maybe this question is, okay, I can see where maybe this question is coming from. So with X-ray, we can't so much control the depth of excitation for the X-rays that we're using. We always have to use an X-ray excitation that's more energetic than what it is we want to measure, because if it's not, we won't excite the signal elements we want to look at. So our depth of measurement is controlled by the signal X-rays that we're looking at. And the way that we can control that is we could look, for example, if we want to control it, we could look at the lower energy line series if that was possible. We could look at the L series versus the K series. The K series might probe 20 microns into the sample, whereas the L series might only probe 2 microns into the sample. So it's a very basic way of controlling it, but that would be the way we would do it by X-ray fluorescence. Okay. I think that's all the questions, and that's good. We are pretty much at our time limit. So, Sue, are there any, again, thank everyone for their attention today, and thank you for attending. Do anything to wrap up with?
No, that's it. So thanks, everybody.
Okay, thank you. Have a good day, everyone.